Hi everybody. This is our first look at a multi-step kind of problem involving efficiency. Efficiency is going to be expressed as a percent. What we're really going to do is do a calorimetry style question to solve for molar enthalpy, and then take this extra step at the end to convert it into an efficiency percentage. One of the nice things about efficiency style questions is they always have the word efficiency right in them. So it's pretty easy to interpret what's going on. Okay. One of the trickiest things about it is there's going to be a molar enthalpy told to us in the question. We need to save it until the end. It's going to be really tempting to want to use that molar enthalpy in the calorimetry part of the question. We need to save it until the end. Okay. Here we go. Here's our example. The molar enthalpy of combustion for propane is negative 2043.9 kilojoules per mole. Determine the efficiency of a barbecue as a heating device if 1.00 grams of propane is required to raise the temperature of a 400 gram knife with a specific heat capacity of 0.503 joules per gram degrees Celsius by 30.0 degrees Celsius. Okay, so first of all, notice the word efficiency is right in the question. As I just said, that's one of the nice things about these kinds of questions. There's a specific word that gives us a signal straight away. Okay. Also notice there's a molar enthalpy in the question. We need to save it. Look, it's right there. The molar enthalpy of combustion for propane is negative 2043.9 kilojoules. We're going to save that number for the end. What are we going to do? Do calorimetry to solve for the molar enthalpy. Okay, so here we go. Calorimetry, negative heat gained equals heat lost. Okay, here, the heat gained, the temperature of the knife is going to go up by 30 degrees. It's gaining the energy. It's the knife. What's losing the heat? We're burning propane. Okay. Straight away, that lets me feel good. The propane is on the heat lost side, and this number that I'm going to use in the end is a negative value. It's energy being given off. This is also combustion. Okay, so here we go. We're going to do calorimetry to solve for the molar enthalpy of combustion for the propane. Okay, that's going to be H equals negative MC delta T over mass over molar mass. Okay, where this MC delta T is the knife. We have a 400 gram knife. There's the specific heat capacity, 0.503 joules per gram degrees Celsius, and the temperature change is 30 degrees. Let's put that in. Negative 400 gram knife, specific heat capacity 0.503 joules per gram degrees Celsius, and the temperature change was 30 degrees Celsius. In the denominator, we have a mass over molar mass. That's coming from the propane. Okay? So this is going to be divided by the mass of the propane, 1 gram, over the molar mass of propane. Let's figure it out. The formula for propane is C3H8. I have my calculator handy. We're not in a rush. That's 3 carbons plus 8 hydrogens. It's 44.11, the molar mass of propane. I set up my calorimetry calculation to solve for the molar enthalpy of propane. This is a little bit weird because it told me the molar enthalpy of combustion of propane in the question, but I'm saving that number until the end. Let me calculate. 400 times 0.503 times 30 divided by 1 over 44.11. Okay, so this is what I got. I got negative 266,247.96. That seems really high, but please, it's important that we realize that this is coming out as joules per mole. Okay? It's important, so now we have our answer, and we're going to divide by the molar enthalpy in the question and turn it into a percent by multiplying by 100. However, we have to make sure that the units of our answer and the molar enthalpy of the question, those match. The question has the molar enthalpy in kilojoules per mole. And so, but my answer here was in joules per mole. So I have a choice. I could convert the number in the question into joules per mole, or I can convert my answer down here into kilojoules per mole. I find that easier. It's going to make this number smaller. It makes them more manageable. So I take my answer, it's here on my calculator screen, and I divide by 1,000. Turn those joules into kilojoules. And I have now a much more manageable number, negative 266.24796 kilojoules per mole. Okay? And now what I'm going to do is my final step. I'm going to take this answer, divide by the molar enthalpy in the question, and multiply by 100 to turn it into a percentage. So here the percent, it's going to equal our answer. It's still just sitting on my calculator screen. I'm not going to rewrite it all out. I'm just going to say my answer. And this is divided by the molar enthalpy that was in the question. This number way up here, negative 2,043.9. Negative 2,043.9 kilojoules per mole, and I'm going to multiply it by 100. So this answer is still just on my screen, and now I'm going to divide by 2,043.9 times 100. What did I get? 13.0264670. A raw answer. I'm going to go back to the original question. There's a bunch of numbers with 3 significant digits. It's very typical, so I need to round off my answer so it has 3 significant digits as well. It turns out to be 13.0%. There is a style of multi-step question, this had 2 big steps, where we're going to have to be asked to calculate the efficiency. These questions are pretty nice. The word efficiency shows up explicitly in the wording of the problem. That's kind of nice. We have a tip. There's going to be a molar enthalpy in the question. Save that until the end. Do calorimetry to solve for a different molar enthalpy. And then we're going to compare those 2 values and turn it into a percentage. Unless we're being told that the piece of technology has high efficiency, if it's something like regular, a barbecue, a stove element, a light bulb, we probably expect the efficiency to be pretty low. And here we're not surprised to see this barbecue only at a 13% efficiency. And I hope that helps.